Happy Saturday and happy data science, happy data or whatever. Let's see. I've not had a little bit of trouble getting set up today. This is one of those times when I'm trying to get up for streaming and like my computer wants to restart and upgrade everything. So it took me a few minutes. I got it already. I don't know if anyone watching actually streams themselves. You might have your own like pre-stream routine. Hey Maddie, you're off to bed. I know it's way too late, but thanks for saying hi beforehand. But yeah, I was just saying my pre-stream routine was quite interrupted today as I was, my computer restarting, Streamlabs, OBS updating, everything screwed up. Well, anyway, let me introduce myself and start the stream properly. I just got to get over that. The past is in the past, and I'm here to stream now. I'm here today to talk about regression optimization in Python and SQL for customer churn. My name is Carl, by the way. I'm a data scientist in Silicon Valley. Yeah, pre-stream routine. Maddie streams. He does a great data stream too, focusing on a lot of SQL data analysis. You should check him out. But yeah, you got to get yourself in the zone. I usually start about a half an hour before the stream, just restarting my computer, which I did today, but then it took like 15 minutes to restart. I believe that restarting first helps prevent stream crashes. But anyway, without further ado, I always start my streams talking and explaining background so that everyone gets on the level set for the topic of the day, which today will be regression optimization. So I'm going to talk for a while, introduce the subject before we get into the actual Python and SQL coding, which will be in just a few minutes. So let's see. Without further ado, what is churn? If you've seen my stream before, you already know. Churn is when customers, subscribers, or followers quit or cancel and don't come back. So no one likes churn. Churn comes from a term called the churn rate, which means the percentage of customers that drop out. But churn is also now a verb. You can say the customer churned or I'm gonna churn. I'm churning from Netflix because I'm reading more books this year. Actually, I'm reading books and I'm not churning from Netflix. But churn is also a noun. You can make a churn report or you can even call a customer a churn. If you say, the customer is churning, they churned last week, they canceled last week, they are a churn. So that's the lingo in the business. What is fighting churn with data? That is a book that I wrote based on my experience as the chief data scientist at a company called Zora. You can get it at Manning Books, and there's a 40% off discount code. Yeah, I must apologize. The book is not that cheap. Don't ask me. The publishers make that up. It's a big book, so hopefully it's worth it. But you don't need the book. You can just watch this stream and get my free source code, and you should have everything you need to fight churn yourself. What is Zora? I said I wrote this book based on my experience at Zora, which is a platform for running subscription businesses. Many businesses that you know run on Zora. Oh, wow, I'm kind of covering it up here. I think I need to actually adjust my desktop a little bit. Hold on, I want to go back because something's not right. What's not right is actually in my stream setup. So I think I mentioned everything was restarting before this stream. And I think my stream desktop, there we go. That's more what it's supposed to look like. All right, I don't want to be covering up all the slides there. That's what was wrong. All right, now you can see me and you can see the stuff that I'm trying to show you over here. So what I was going to show you was Zora customers include Zoom. I was covering up Zoom, so that's when I noticed that I'm covering up the slide. I'm covering up Zoom. And Zoom is another company which is, became a noun and a verb this year because everyone is on Zoom meetings due to the pandemic. But Zoom is a Zora customer, so that means they manage their subscribers and their subscriptions on Zora. So I worked with a lot of these customers on their churn cases, and that's how I got the experience and the techniques I developed that I put into this book. Because churn is different from a lot of other problems. Here's my next pitch. Why should you learn about churn if it's so different from other problems? Because churn is the most common data science problem in the world. I challenge anyone to tell me a more common problem, because every company in existence today has a churn problem. Everyone wants to keep their customers coming back, because business is all about relationship, ongoing relationship with your customers today. But churn is special. There's some special techniques that you need, and if you study with me, you'll learn to do it from raw data to actionable results. Now, what are actionable results for churn is reducing churn. So this is not a Kaggle competition. You don't just want to predict churn with high accuracy. You want to reduce churn. How do you reduce churn? Make a great product. That's always my favorite. If your product doesn't suck, people won't churn. Well, it can suck a little bit, but you have to be better than the competition, right? Also, you can do some marketing with your existing customers, keep in touch with them, tell them about your product, etc., etc. You do customer success and support, which means helping out your customers, whether they know they need it or not. And also, you've got your sales and pricing to right-size your plans and discounts. At this point, I want to call out to anyone in the chat, how's the music volume? I like it if you can hear the music, but it's easy to hear me. So if anyone has any feedback, turn it up, turn it down, let me know. I think my, the Spotify channel I stream, sometimes the levels vary. So anyway, so that's what data-driven churn reduction is all about. So let's look at some real data since I've just been talking. I gotta get into some data to show you that this is not a chatting stream. This is a science and technology stream with live programming. So the data that we have to fight churn is in a database. Yes, of course, it's in a database. If you're working in the business, pretty much all data lives in databases. Someone in an interview was asking me well, why do you use, Scott Edwards, maybe a bit high, better. Oh, music level too high? Let's see. I think you mean the music level is a bit high. Let's see. I will try to reduce it a little bit. I took 1 decibel off the music level. Let's see if that's good. So I didn't get set up in my database here. I want to look for the search path. This is what I'm going to do. This is a Postgres thing. You start out with setting your search path. And for me, it's SocialNet 2. If you're following along with book code from the book, you probably got, yeah, not me, haha, and not me too, right? Not live streaming, of course not. Who would do such a thing as live streamed buzz or high? That would be very, very reprehensible if anyone were to do that. I'm sure no one on Twitch is doing that at all. Anyway, so I want to show you the data that we have for fighting churn. And it starts with what I call events. I'm looking for an old query I can use to demonstrate to you. Here we go. Here's an event query. I'm going to select from an event table, and I'm just interjoining on the event type table. That's a little bit small. And this will show you the basic data. Whoops, don't select the query when you execute it. This is the basic data that we get for fighting churn in this project, where we have a bunch of events at certain points in time, shown by the time, and we also have the account ID, which shows that each event is tied back to an individual customer. Now, this data is from a simulated social network, so it's not real. This is not real customer data. Relax, people. Everyone's PII is safe here. This is simulation, but they have events like it were a real social network. Liking, they do have ads on this social network. They also have messages and replies. So you do all these things on the social network, and that's what we observe our customers doing. And then we analyze this data to see who churns. Now, the first thing we did with this data in earlier streams, I'm just going to go look for old queries here, is we calculated metrics. So now I'm going to select from the metric table, and there's a metric name table, similar to the event table we just looked at. But once again, don't select part of your query when you hit that execute button. Not in this SQL tool anyway. I mean, they generally consider that a feature, right? That you can select part of your query and execute it. But anyway, so metrics are calculated summaries of the events for each individual customer. And we've already calculated those on old streams. So I'm not even going to go back and tell you about calculating metrics. Everyone who watched my streams before is super sick of calculating metrics. Although, you should never get sick of calculating metrics or creating features for your data, because if you're into data science and analysis, it's just what you spend most of your time doing. So the metrics summarize the events. So this metric, like per month, and this value here, 4, means that this customer had 4 likes in the last month as of this date. Hey, Ed Tavares, welcome to Data Streaming Saturday. It's Saturday afternoon for me, and for Scott, who I know is in Pacific time. Anyone else in the world where you are, give us a shout out. Let us know what time of day it is. Maddie is in Central European time, which means it's like night, like go to bed time. So we already calculated all these metrics. Saturday night for you in Brazil. Oh, cool, Ed Tavares. You know, I said I worked at Zora, and the truth is I'm at a new company now, and we've got data scientists in Brazil on my team. It's very cool. More about that some other time. But so I happen to know Brazil is about 5 hours ahead of me, because like I said, my team is on Brazil now, some of them. So this is the basic data for fighting churn. I should get moving forward, or we're never going to get to the new stuff. So if you want to do this yourself and follow along with the code, it's all in a GitHub repo shown here. You actually need to run a data simulation to produce all that data that I just showed you. Maybe I should post a database that you can just download with all the data, but it seemed easier for someone to run their own script and populate their own database. So to get all that data, you got to run a simulation, but all the instructions are on the GitHub site. And after calculating all the metrics, what I did in earlier streams is we made a data set. And let me show you what the data set looks like, I guess. For anyone who's never seen a data set, I will show you a data set in Microsoft Excel, which is a fairly convenient way of showing people stuff. Let's see, this is an old data set. This one actually, this isn't the very good one. This one only has a few of the customer metrics, but it shares the characteristics of all data sets, that each row of the data set is one observation that includes multiple measurements for the same customer, right? I'll just show you this to like give you a sense of what a data set is. So here, customer 112 on February 9th, they did not churn, and they had all these customer metrics. Now this is different from the customer metrics we looked at in the database, because here they're stored all in one table for all customers, and you have the same metric all stored in one column. Well, you can only see like per month here. In the data set, we've flattened the data to one customer observation on each row. And we did that in previous streams too, so I'm not going to go into creating the data set today, or the people who have watched me before would be bored. Hey, Alejandro Close. 11:13 in Barcelona, Spain. I love Barcelona, by the way. That was my favorite city to visit in Europe, because it has everything. You know, beach, culture, nightlife. Barcelona's awesome. Yeah, well, Ed Tavares, good luck on pursuing your career in data science. So you're graduating in product engineering. That's interesting. Well, data science is a new field, so a lot of people transfer into it, you know, from other, you know, areas. So anyway, now this is a summary of the data set that we've got going so far. So there's actually more metrics here than I just showed you, and we spent weeks on my stream building up this data set by calculating the additional metrics. So we have the basic counts on the top, and then there are these ratio metrics where it's like add view per post, reply per message, like per post, and those are actually exploring the relationship between different customer metrics. And in this table, I'm showing you what percent of customers have each metric. So there's also the churn rate on the first row. That's actually not a metric, but that comes in the customer stats. Now this is listing 5.2 from the book, and I need to demonstrate some code soon. So let me know, does anyone want to see listing 5.2 to make a table of statistics like this? It's actually pretty basic Python. We can get into that. But let me tell you more about the data set, and then we can decide what code to demo first. So this summarizes all the metrics we have in our data set. And then we did a correlation analysis. This was also from a previous stream. And we saw that some of the metrics are highly correlated. Like ad views, likes, and posts are very highly correlated, shown up here. This next row is unfriends and another metric we calculated, which was unfriend per new friend. And then messaging and replying is also highly correlated. And that all came out of a correlation analysis that we did, also in earlier streams. So like I said, this is the part of the stream where I'm catching up everyone on what we did in previous streams before we get to actually, some new stuff. But I'll do some coding soon. So because of the correlations, we did a little dimension reduction or clustering of the data, which is grouping together the highly correlated metrics using pretty basic criteria according to the correlation matrix. So we had group 1 for ad views, likes, and posts, group 2 for unfriends and new friends, and group 3 for replies and messages. And this was done with the code listings 6.3 and 6.4. All old history from my streams, which you can see, in the old streams. So what's next? Should I demo one of those listings? Regression result, listing 8.3. Maybe we should demo this one, because this is the one we're going to be moving forward on. And this is what we did in the last stream. So this will be a good place to start. This was what happened when we ran the regression, which, as I explained in the last stream, is a way of analyzing how much each of these different types of behaviors contributes to customer engagement and churn. And as a result of the regression, you get a weight or coefficient on each metric, which is shown in this column. So metric group 3, which is messaging and replying, got a very large coefficient, 0.7, and new friend per month also got a high weight or coefficient, 0.7. And I also explained last time that these translate into the impact on retention and churn, in the sense shown in this second column, that so metric group 3, messaging and replying, 1.3% on that metric means that a customer who's one standard deviation above average has a 1.3% higher retention probability, or 1.3% lower churn probability, because it's the same thing. Let's run this listing to demo everyone who didn't see the last stream, and then we'll go on to the new stuff. So let's see. I need to get to my regression listing. Let's see, it was supposed to be, what did I say it was? 8.3. Maybe I have these mislabeled. I usually do. This one says current customer. But that sounds like it's regression. I'll check the code first. Let's open it up and figure out what's happening here. So this is the code from Fighting Churn with Data. If you look at it, you'll see there's a folder that has listings, and then each chapter in its own subfolder. I guess that makes them modules in Python. I'm trying to improve my Python speak, so I think these are modules. So let's see, it looks like Chapter 8, Logistic Regression is 8.2. I knew that was wrong. So, okay, don't listen to my slide. It's really 8.2 for regression. So let's find the right one here. Here it is. See, I already had one for regression. All right, and this other one, 8.3, was supposed to be, what was it? Stats or something. We'll get to that later. Sorry. I'm not quite prepared for these streams ever. Not really. I mean, I try to prepare. So anyway, let's look on what happens when we run the logistic regression function from the book. Now this is actually a wrapper around logistic regression from sklearn. So that's the first thing to understand, is that we're not implementing regression here. We're running it and analyzing it. So I'm just going to hit the run button now, and we should stop at my breakpoint. So the first step in running a regression is preparing your data, which in this case means loading the file that we already saved. I'll just step through this really quick because we're going to use this function more later without really getting into it. This just loads the data from a given path. I check the path exists. And this has to be the grouped data that I described earlier, meaning the dimension reduced data. So then I convert the is churn column to a bool to make sure that it's a boolean in case it wasn't loaded correctly. We're actually analyzing the regression in terms of retention. So there's this variable as retention equals true, which is kind of an optional. You can either predict churn or predict retention. But it's easier to predict retention because then your positive coefficients correspond to good things. Like I was showing you, we'll go back to the table of results in a minute. But if you predict churn, then a positive weight or coefficient is bad because it's predicting something bad, which is churn. And it's just more intuitive for people to predict retention. So I actually, in this case, invert it to predict retention. And that's all the data preparation we're doing. Next, we create a logistic regression object from sklearn. We use this particular penalty and solver, which is a modern form of logistic regression called ridge regression. And then we fit the regression. And that's actually it. That's how you run a regression. Now, the rest of these steps are actually saving out that summary that we looked at. I'm not going to go into it on this stream because I went into it in gory detail last stream. So here I'm just going to call save regression summary. Oh, damn it. I had another breakpoint. That was from last stream. Step out of save regression summary. We went into that last time. Then we save the regression model, which is, I'll step into that because we're going to look at that model later. I just pickled it. And if you know Python, pickling is just saving out an object in, I guess, like a binary. And if English isn't your first language, pickle means preserving food. You might have heard of pickled cucumbers are the most common type of pickle. And in English, a lot of times people say pickle. They mean pickled cucumbers, but it's also for any kind of food that you save. And so this just, dumps it out, and we can reload it later. And we also do some predictions, but this is really all I wanted to show you. Just the basic logistic regression saving, because we're going to get into more details on logistic regression basically right now. Let's see. This was the last thing I said. Regression results. So what else was I explaining here? So now we saw... someone from work is like slacking me. Hold on. I have to tell, that's a long story. Don't ignore that. Pretend that didn't happen. I'm just going to keep on doing what I'm doing, which was explaining the regression results. So when we look at this, add view per post has a negative weight or coefficient of 0.48, which came out of that regression. And this minus 1.5%, that means if you're above average in ad views relative to posts, then you have this negative impact on your retention probability. So that's why I was saying that bad things here get negative coefficients and have negative impact because we did the churn regression in terms of retention. So that was all that. And here you can see at the bottom the baseline. This is actually important, 97%. That's the baseline average customer retention rate. So you might remember from previous slide, the churn rate was actually around 5% here. That's like one kind of baseline. But another baseline is the average customer churn rate, which is 97%. So your average customer is actually better than your average churn rate, which makes sense if you think about it because of the long tails and extreme outliers in the data. Okay, so I think I've re-explained the regression results. And this is important because we're going to look at a lot more of these in just a moment. Now here's something I forgot to show you in the last stream when I prepared it on regression. This is a real case study result of a regression for a company called Broadly. And Broadly is a software as a service product that small businesses and medium businesses use to manage their online presence. It includes getting reviews from customers and getting your customers to review you on Google and Yelp and services like that. So a lot of small businesses use Broadly to manage their online presence, and Broadly was gracious enough to let me present some of their data in this Churn case study. So if you're a business that wants to manage your online presence, do check out Broadly. This is my plug for my sponsor. My sponsors are really the people who let me, show you their data and their churn results. So that's my plug for my sponsor, Broadly. Now let's look at their regression results. Now they had a lot more metrics in their data set. Now the data set I show you from the simulation only has 10 or 15 customer metrics. A real case study typically has many, many more, as you see here for Broadly. Their first metric group consisted of 22 metrics that had to do with messaging, adding customers and messaging them. And that got a regression weight of 0.16. And metric group 2 for Broadly also consisted of 22 more metrics that all had to do with the reviewing process, getting reviews, asking for reviews, getting good reviews, getting bad reviews, and those had a very high weight in the results. So these are very strong in predicting that customers will stay. Now the thing to note about this is because there's so many metrics, there's a lot of results here. There's a lot of groups. There must have been something like 50 or 60 metrics. You can add it up later. So there's all these groups, and a lot of them have a lot smaller weight too. So after these first couple of metrics which have large weights, there's a lot of metrics with small weights. There's a few more with large weights. Actually, over on the right are some metrics that we looked at in earlier streams. One is account tenure, which means how long the customer has been a customer. And that has a very large positive weight. So for Broadly, like many companies, the longer a customer has been a customer, the more likely they are to stay a customer. So that's why you see a high weight on account tenure. Also, we analyzed billing period for Broadly in a previous stream, and we saw that customers who pay annually once a year or every 12 months have less churn than customers who pay every month. So that's why billing period also has a positive weight, reflecting higher retention for 12-month billing period, because the billing period is coded monthly. And lastly, we also looked at a metric called detractor rate for Broadly earlier, which had a moderate negative weight. So the thing this illustrates is that when you do a real regression, number one, you really have to do dimension reduction, because this result is already kind of too much info. If we hadn't grouped together these 44 metrics at the top, then this would be like scrolling across pages and there would be too many weights to make sense of. It also generally doesn't make sense to look at a lot of correlated metrics. This also illustrates that one of the things you have in regression is you have a few metrics that get high weights or coefficients, and a lot of metrics that get low weights and low coefficients. So there is an example of a real live case study, logistic regression for churn analysis. Anyone on the chat, of course, let me know if you have any questions or want me to say more about anything. Sometimes I think I talk too fast when I'm trying to get to the new, coding and material, which starts now. So this is what I wanted to talk about today, which is controlling the regression. There's a parameter that influences the regression, because we were talking about this problem of having a lot of metrics with low weight, low significance, which you can see here, in the Broadly and also in the simulation. We have some metrics with strong weight, but then it also puts out these 0.01, 0.02, and those are just distraction, and they might even make your model worse by including them. So by using the C parameter, you can control how much weight is available to distribute across the different features or metrics in your data set. And when the C parameter is high, you have more and larger weights coming out of the regression. And when the C parameter is low, you have fewer and smaller weights. So it's a parameter. And we'll face the problem of how do you choose the C parameter is that you experiment with it. Because you want to minimize those unnecessary weights. and maximize accuracy. So, how do you use the C parameter? I believe it is time to get to some more code. So this will be listing 9.4. So I'm going up to chapter 9 in the book. And let's close up basic logistic regression was 8.2. Now we're in chapter 9. So I've already got it open here. Regression C param. Now, why is the parameter called C? That's a good question. Does anyone on the chat know why they would call this parameter C? And I'm going to give you a spoiler alert. It doesn't make any sense, I think. Unless someone can explain it to me better. I think the C parameter name is actually kind of a misnomer, at least in this Python library. So here's another regression function that will use the C parameter variable. And you can actually see I'm importing from my old listing, from listing 8.2, import those other helper functions we just looked at. Prepare data, and also save regression model, save regression summary. All those helper functions we were using in that previous regression, we're going to reuse. So those were my own helper functions. And of course, we're also using logistic regression from sklearn. So, as usual, I need to make a new configuration. That's just the way I run this code. Always by copying my old configurations. This is going to be C param regression. So I said this was listing 9.4. You might have noticed I skipped a few. You might be wondering, what happened to listings 9, 1, 2, and 3? Well, don't worry, I'm not gypping you on the listings. We're going to get back to those later. Although I shouldn't use that word. That's actually like, a bad word to say. People used to say that all the time, but it's actually not a nice word. So I am just going to not make you miss out on any listings. We'll get back to those. So let's see, regression C parameter, ready to run it. As you can see, there's actually very little difference. Oh, I think I need a version actually. That was the one thing I forgot. I need to do a version. So regression C parameter, I want to actually run a version. So let's first run version 1. And we will see what happens. All right, so version 1, what happens here? We are coming into the regression function, hopefully, assuming everything works, nothing breaks. Okay, so here we are. I've got the C parameter now set to 0.02. And in the meantime, has anyone had a guess as to why it's called the C parameter? Going once, going twice. Anyone can guess why it's the C parameter? Anyway, we call the prepare data function, just like before. And now the only thing I'm doing different, is I'm putting in the C parameter here. Thank you, Ed Tavares, for at least letting me know that I'm not talking to myself. Not a clue. It doesn't make any sense is the thing. I'll start telling you in a sec, as soon as I show you. So I passed in this parameter, C. That's it. Everything else about the listing is exactly the same. I'm just going to let this go. The one thing it's going to do a little bit differently, I'll show you, is when I save... Oh, I actually missed it. Notice that I'm passing in the C parameter as an extension, as an extra parameter in these functions, right? That was actually crucial. So now, when I save my regression result out, which is what I always do here, I have tagged it with the parameter C that I used. And let's look at what happens when we use the parameter 0.02 instead of the default. I believe the default is 1. Lo and behold, when I show you this result here, now instead of all of the different metrics and features getting a weight from the regression, we actually have some zeros. So now dislike per month got a 0, post per message got a 0, and new friend percent change all got zeros. Where if we look back in the old regression, back here, these all had weak things like post per message, new friend percent change. These had very weak weight in the old regression, but now that I use the C parameter, we've just zeroed them out. So that is what the C parameter does. So why is it called the C parameter? I think it's because it's related to a parameter called the cost, meaning you include a cost or like a penalty in the regression that makes it more costly for the algorithm to give the weight to each variable. So it's like a constraint on the regression, an extra term that you assign a cost to the weight so that it tries to use less of it. Now, the thing that I said is higher C means more and larger weights. Lower C means fewer and smaller weights. So why is it cost? Actually, the cost in the algorithm is 1 over C. So it's actually the inverse cost parameter. So if you take 1 over the C parameter, that's the cost. Now, I find it really confusing because we have a parameter that's C for cost, but the higher you make it, the parameter, the lower the cost. And the lower the parameter, the higher the cost. So it's actually really confusing. I think it's supposed to be C for cost, but it's actually the inverted cost or the reciprocal cost, or, so I find it very confusing that they call it the C parameter for cost, or cost parameter. So I just call it C. Now let's look what happens when we use a lower value for the C parameter, which we'll now do by going in here and changing the version number. We'll go to version number 2. And if you're wondering how this works, I'll show you. There's this JSON, which is a configuration, which shows you what each version is. So let's see, version 2, it says here, had cost parameter 0.01, and I guess the default in version 1 was 0.02. So now version 2, as we'll see, is going to have 0.01 cost parameter, and we'll see what that does to the weights. But I'm still going to, hit the debugger just to prove it to you here. See C param now 0.01, and now I'm just going to let it run. Now let's look at the result. When we go down to the 0.01 result, let's see, actually, wow, it doesn't look that different. Well, it is kind of different. Let's look at it more closely. I was actually expecting this to be a little bit different, because this is saying that there's still only 3 zeros in the weights. But you can actually see that the weights are getting even smaller. Let me format this a little bit differently so you can see it clearly. So in the first version, so changing the C parameter doesn't always make more zeros in the weights. Is C specific to ridge parameter? Is C specific to ridge regression? I don't think so, actually. I think it's because, yeah, you have a cost parameter in the other versions of regression. So I don't think it's specific to ridge. And now Ed Tavares, C parameter is almost like reinforcement learning where the agent gets a penalty or reward. Yeah, it is a penalty. It's definitely a penalty. Except I think it's like 1 over the penalty or, something like that. So let's see. So thank you. Hope that kind of answered the questions. Whoa, I formatted that as money. Look, it's all like dollars. That's not right. What I wanted to do was just make these kind of like normal numbers so you can see. So you can see that when I lowered the parameter to 0.01, these weights got somewhat smaller, although I didn't get more zeros really. So let's actually go to the next version and use an even higher C parameter. Let's see, this will be version 3. We can just like keep cranking it up, I'm just gonna run the script now, and I'm just gonna look at the results. Gotta pick up the pace here. So now we're down to 0.005 on the C parameter. And I'll open up this new one. All right, here's the 0.005 result. Now you can really see the effect kicking in. of this C parameter. So now we have mostly zeros, actually. That might have actually been going too far in this case. We went so far in the C parameter, we now have 0 weight on the first 2 metrics, which were kind of important, actually. So I think we might have gone too far now. It's funny, this is coming out a little bit different than when I did it in the book. But I think this shows you the point. You can also see the highest weights are now down to about 0.4, 0.5. And so it's reduced the weights all over everything. So that is showing you the increasing influence of the C parameter on a regression. And I don't think I have any more versions pre-programmed. That was version 3 using 0.005. Okay, so those are all the pre-prepared versions. We can do one more though. Let's just do it. I'll show you how to enter a new parameter here. I'm just going to make a new version for this listing by tagging it a new entry into the JSON. It's giving me an error because you can't have the same key twice. JSON is just like Python dictionaries. So now let's go down to 0.0025. I'm dividing it by 2 in each case here. Let's see what happens. This is going crazy here, getting really low on that parameter. But you notice how I reduced the parameter by dividing it and by dividing it, because it's a parameter where the influence of it depends on a big range of magnitudes. So you have to search for the best parameter over multiple orders of magnitude. All right, now we've got a really low parameter, I think. Wait, I think I did it wrong actually. 0.00. Is that right? No, that should be right. 0.0025? Okay. I thought I did 0.02, because this is showing me 0.02 in the thing here. I feel like I did the wrong version. Something's wrong. This should be... I'm going to have to debug this again. 0.00. If anyone sees my mistake, let me know. So Ed Tavares says, so you're trying to balance the C parameter, you want to lower the relevance of some things, but you want to exaggerate. Is that right? Well, I don't know if, you kind of want to focus on the things that matter the most and not focus on unimportant things. If you're already a data scientist, you know there's something called overfitting, which is when you use irrelevant data to try to fit your model, you get worse results because the algorithm will just fit noise to the data. So this is really a way of preventing overfitting, which means using kind of irrelevant stuff in your model. I'm trying to figure out why this last example doesn't seem to have worked, because I'm saying here it should be 0.0025, but then let's see what it says here. 0.02. Now, something's screwed up. Because I said, I feel like it's not working. Why is this not working? Well, don't worry, I won't belabor this. If this doesn't work in like a second, I'm just going to give it up. I'm saying version 6, right? This is how it's supposed to work. I might have just found a bug here. I don't know. Things just never work sometimes when you're live streaming it. Said chapter 9, blah, blah, blah. Oh, I know what the problem is. I'm in the wrong parameter file. Oh, see, this one says SocialNet 7. And I actually need to be... I'm in the wrong parameter file. I'm sorry, people. That's what I get for, hacking around. So this is where, I'll show you where these configurations are saved. I need to get in this version, and then we'll get it to work. All right, now I got to get back down to chapter 9. Let me find all the chapters and really get the new configuration in. Okay, chapter 9, listing 4. Now I'm in the right configuration file, and I'm just going to go in here and paste in that new configuration. Whoops, that looks screwed up. There we go. All right, now let's run this, and now we should have the 0.002 result waiting for us. All right, there we go. Now let's see what using even lower C parameter takes. And I just debugged my script. All right, so you're still looking at the old result there, because they always open up in my other window. Here's the new result with even lower weights and fewer non-zeros. So now this is probably going too far. I think we've set too many weights to 0. So the next subject is really, okay, we did all this and we added another version. The next question is, how do we choose what value of the C parameter is the right one to use? So this is actually getting really into Ed Tavares' question is, how do we find the balance? Where is the best value of the C parameter? So I say minimize the unnecessary weights, but maximize accuracy. So how are we going to maximize accuracy? We are going to talk about accuracy because we need to say, what do we mean by accuracy that we're going to optimize? And now I'm going to actually go into the subjects from the earlier part of chapter 9 in the book, which is how do you measure accuracy for churn? So you've all heard of the word accuracy, hopefully, and accuracy has both a general and a specific meaning. The general meaning of accuracy is just like how correct something is. But there's also a specific meaning for accuracy, at least in English. There's one particular metric, which is what is meant by accuracy. And I call that the standard accuracy to distinguish it from the general concept of accuracy, because we're going to look at more than one version of accuracy right now. So we're going to start with the standard one just to get that out of the way. Standard accuracy is illustrated in this picture. Now suppose you have a bunch of customers shown here with their little smiley faces. And I don't know if hopefully you can read this. They're shown in order of increasing risk from left to right. So you've got more happy faces down on the left. And if you look closely, you've got more sad faces on the right. And the way you measure accuracy is as follows. You are going to predict who is going to churn and who's not going to churn. And here I'm illustrating that with a dashed line. So in this case, we're going to take our 5 most at risk customers. This is a toy illustration. And we're going to predict that they churn. So I'm predicting that these 3 customers churn and all the rest don't. These 5 customers churn rather, and all the rest don't, because these were my most at risk customers, right? Now the actual churns are shown by the red X's on them. So we had 2 actual churns in our predicted group on the right, and then we had 3 actual churns overall. Now you measure accuracy by looking at true positives and true negatives. A true positive is someone who we predicted to churn and they churned. So these 2 people up here are the true positives, because we said they were going to churn and they did. And all of the ones on the left who did not churn are the true negatives, except for these 3, because those are the ones who we said they're not going to churn and they did. So in this case, the accuracy is defined with this equation. Now I hope a little bit of math doesn't freak anyone out. If you don't want to do a little bit of math, then I don't know, hang in there. We'll get through this in a minute. But a little bit of math is necessary here. So here, the accuracy is the number of true positives, which is 2, plus the number of true negatives, which is 42. Because remember, on the left, everyone who didn't churn is a true negative, and only those 3 who did are the false negatives. Those are false negatives because we said they weren't going to churn, but they did. So true positives plus true negatives in this case is 44 over 50, or 88%. Now, let's ask you, is that a good accuracy or a bad accuracy in this case? Because, well, it's a trick question. This is actually not a good accuracy for this case. And it actually illustrates why accuracy is a bad metric for churn, or at least the standard accuracy is a bad metric. Here's why. Let's say you want to cheat on accuracy for a churn problem. Now, in the last slide, I said we predict the 5 most at risk would churn, which makes sense. We had to predict someone's going to churn. Or do you? Because here, let's say we don't predict anyone churns. So my new prediction is that no one churns. That's why I have no line. Remember on the last one I was separating them? So here was my line separating the churners. Here I didn't draw a line. So here I'm saying no one churns. That's my prediction. And what's my accuracy? Predict that no one churns, and you get accuracy of 0 true positives. You have no true positives because you didn't predict anyone would churn. But you have 45 true negatives because you predicted no one would churn and only 5 people did. There are 50 people in this toy problem, by the way, if that wasn't obvious. So here we have 90% accuracy by predicting that no one would churn. So now that's not a very good metric for churn because you can game it, you can cheat. That's why I call this the cheating on accuracy for churn slide. So you actually don't want to use accuracy to measure your churn models. Okay, what do we use? We're going to use different measures of accuracy other than churn, which is why I distinguish at the start between what I described as standard accuracy, which is this particular metric, true positive plus true negative over total, versus the general concept of accuracy, which is just how correct it is. Now, what's another way to measure the correctness of the model I'm about to present to you? It's called the AUC, which is short for the area under the ROC curve. But we're not going to actually go into that detailed definition. I'm just going to explain to you what it means in this one slide. So, measuring the AUC of a prediction model is equivalent, or of a regression model, or any model, is equivalent to doing the following. You have all your non-churns, which in this case are these 45 people, and then you have all of your churns, which in this case was 5 people, because that was, remember, that was our setup here. We have 50 people, 45 non-churns, 5 churns. To measure AUC, you take the forecast of every churn and compare it to every non-churn. And what you want to find is that you predict that the churn had a higher risk than the non-churns. That's why I show them here on like a scales. So you compare your prediction for every churn to every non-churn, and you look at the percent of time where the true churn received a higher risk forecast than the non-churn. Now, how does this solve the problem of accuracy? The problem with the accuracy, in a way, is that there weren't that many churns, right? The problem with accuracy for standard accuracy for churn is that the true positives can only be a small number because not that many people churn. And AUC improves that by comparing every churn to every non-churn. You make the most possible use of your churns. So that's actually a lot of comparisons if you think about it. Because if you have 5 churns and 45 non-churns, then you have, well, it's 5 times 45, something like that, comparisons. It's not exactly, because that's considering the order. But so you have a lot of comparisons between churns and non-churns, but it's done automatically for you in an algorithm. So let's actually measure the AUC, or the area under the curve, for our churn model. Oh, it looks like I had some animated arrows that I forgot to trigger. Great. All right, let's now go back to listing 9.1 and see how to measure AUC in Python. And this will be very easy, actually. Let's see, this is, once again, copy my listing. I'm going to call this 9.1, and this is regression AUC. So now I want to go back to listing 1. All right, so now we're going to do chapter 9, listing 1. Let's open it up and put in a breakpoint. And you'll actually see it's very easy to measure regression. But we're actually also going to see loading the model up. Maybe I should debug into that real quick. So let's go into listing 9.1. So here I am in my function already. Or am I? There we go. Now I'm into it. So the first thing I'm going to do is reload my regression model. That's the regression model we saved earlier. And I'll just demonstrate this once because we haven't done it. This is how you load a pickle. It's really just making the pickle path. You have to open the file first in binary mode, which is shown here. And then you get the regression model. There you go. Ta-da! Now I have a regression model. That was easy. Now I'm going to prepare my data to do a prediction. That's, again, using the prepare data helper function, which we saw earlier in the stream. And next we're going to do predict proba, which means predicting the probability of the outcome. It's actually important for AUC and for churn in general. You should use predict proba and not just predict. The plain predict method will give you a binary outcome, yes or no, who churns. But most of the churn prediction use cases actually need the real valued outcome. So that's why I always use predict proba, for a churn problem, or many problems you care about the relative prediction and not just yes or no, right? So anyway, so this gives me my predictions. And if we look at the predictions, you can see there are going to be a bunch of numbers. I had 24,000 people in my data set, so 24,000 predictions, and here they are. It gives you two columns. The first column is the negative outcome, which in this case is churn, and the second column is the positive outcome, in this case regression. But each row is for one example or one customer. So that shows you running the predictions. Now, how do we get the AUC score? Oh, look, I just used the ROC AUC score function, which comes from sklearn.metrics. So here I'm not actually showing you how to calculate the AUC, and it's actually kind of technical, and you would only get into that if you're really into stats and math. But so I'm aiming this towards people who want to fight churn without doing too much math. So let's just say we get the AUC, and that's it. Now I have my AUC score, and in this case it is 0.79, as you can see. That might be a little bit small for you to see. Can you all see that? Well, anyway, it's 0.79, and here I also print it out. So this is kind of like a do-nothing listing, actually, in the book. All it does is prints out the AUC score, which is 0.8, roughly, in this case. But this is really just a demonstration, because later in the chapter we're going to use the AUC more for other things. But that just shows you how you calculate it in Python. Now, the next thing you might be wondering is 0.8 AUC good or bad? Now, how do you know? Well, I provide this convenient table, and this is in the book in chapter 9, to kind of give you what in my experience, are reasonable ranges of AUC scores for churn prediction. Now, these ranges aren't necessarily the case for other types of problems, because different types of problems may be more or less predictable. So here's what I say is the first thing actually to remember or understand about AUC is that 0.5 is equivalent to random guessing. Why? Let me go back. So the AUC is the percent of time that you said that a true churn would have a higher risk than someone who didn't churn. Now, if you had 0.5 on this test, you would be 50-50, or it would be the same as flipping a coin, random guessing. So 0.5 is basically random guessing for AUC. Now, a little bit better than 0.5 is kind of like, and I say 0.45 to 0.55 is like a range in which it's not that much different from random guessing. Now, a little bit better would be 0.55 to 0.6 AUC, which, as I say, is better than random guessing but not good. Then most churn prediction problems that I've worked on have AUC in the range from 0.6 to 0.8. And that's kind of the typical range that I see for churn problems. But I don't really see AUC much higher than 0.8 on churn problems, just because churn is hard to predict. And if you find a churn prediction case where churn is much more predictable than 0.8 AUC, I would actually be suspicious that there's something probably wrong with your data. And that's just because human beings are really random. And people churning or not churning is just like so random sometimes, you really can't tell. So if you have around a 0.8 AUC, that's very highly predictable churn, at least in my experience, of real churn case studies. And if you're much higher AUC than 0.8, then yeah, it seems suspicious. Now what about AUC below 0.5? Here I say something is wrong. The model is predicting backwards. Because that means you're consistently predicting that the non-churns had higher risk than the churns. And a very common problem in that case is that you're using the wrong output from predict proba. Remember, we looked at the code a minute ago. Where am I? This is the wrong file. This is it. So we had predict proba, and as I showed you, it had two columns of output, one for the churn probability and one for the non-churn or retention probability. So if you find your AUC is much less than 0.5, check that you're using the right column from the output of predict proba. All right, now that's one metric for measuring the accuracy of churn models. Now remember, we're doing this because we're going to optimize our regression. There's one more metric of churn accuracy I want to show you while we're at it, which is called lift. And it's good to know because business people like it. Lift is also a model where you assume that you predict some group that's most likely to churn. In this case, you take the top 10% of people at risk, kind of like in that original accuracy, but we're going to calculate the metric differently. The lift is the percent of churn in top decile most at risk, which is the top 10% of your risk forecasts, divided by the overall churn rate. So in this case, the lift is 40% over 10%. Why 40%? Because in the top decile, most at risk, which is this group here, we said, we had 2 churns. So 2 out of 10 churned in the top decile, which is 40%. And then overall, there's 10% churns, which is 5 out of 50. So in this case, the lift is actually 4. Now that's actually a pretty good lift, as I'll show you in a minute. But first, let's look at calculating lift. So we're going to calculate another accuracy metric, also using regression. And so now we'll go to listing 9.2, regression lift. And in this case, as you'll see, let's get to 9.2. We're actually going to calculate the lift ourselves after I put in the breakpoint. So I am capable of writing an algorithm from time to time. And I implemented my own top decile lift function because no one else had seemed to have done it yet. So just like before, we're going to load the logistic regression model. We're going to prepare the data, and we're going to make the predictions. But now we're going to call the calc lift function, which is actually just right up in this file right here. So I'm just going to go into this function, come out up here, and now we're going to calculate the lift. Given we've got a series of the true Y values, which means who really churned and who really didn't churn. And we've also got the series of the predicted Y values. So the first thing I do when I calculate lift is I make sure there are a decent number of unique predictions. Now why? Because recall that lift requires you to separate out the top 10% most at risk from your customers, which means you must have assigned different risk values to your customers, which seems intuitive, right? That's what we saw when we did the predict proba function before. However, you can get into trouble, and if you screw up your model or do something wrong, maybe this has happened to you. Have you ever run a model and gotten everyone to have exactly the same prediction? Come on, anyone who's really a data scientist out there, this must have happened to you at least once, right? You get the same prediction for everyone in your data set. Now, why does that happen? it means you use the wrong parameters. Bad parameters for your model could give you a condition of everyone having the same value. So what I do here is I just check that there are at least 10 unique predictions. And if there are fewer than 10, I just return 1 for the lift, which is a very bad lift. So here I actually have many unique predictions. Actually, we can evaluate this. We have a lot of unique predictions here. They're all unique predictions, so it's all, kind of ridiculous in this case. But that's a good check for the validity of your data before calculating lift. Now, the next thing I do to calculate the lift is I sort the customers by the predictions. And I'm using a list comprehension of a sorted zip. So this is some real Python hacking one-liner here that sorts all the customers by the predictions. Next, I calculate my overall churn rate, which in this case is just the number of true Y values, which is, true churns, divided by the overall length. So in this case, the overall churn is 0.05 or 5%, which we saw earlier in the stream looking at the statistics. Next, I want to see where is the 90th percentile, because this is supposed to be the top decile lift, which means you take the top 10% of the customers. So now I just want to see where in the data does the top 10% start. Because I have around 24,000 rows in the data, the top 10% starts at, 22,000 something. So now I count the number of churns in the top decile using this list comprehension and a sum. So I sum a list where I take the outcome, which is the first value, in the top 10, which is the sorted by prediction from the 90th percentile to the end. So that gives me a count of 574 churns in the top decile. And now my top decile churn rate is the number of churns in the top decile divided by the number in the top decile. So in this case, my top decile churn rate, if you can read that small number, was 0.23. So now we have all the ingredients necessary to calculate the lift, which is the top decile churn rate and the overall churn rate, which was up here. And in this case, my top decile lift is 4.5. So that is how you calculate the lift. Now, why is lift a good metric to use? Actually, I'll tell you, it's because people in business understand it really easily. It's actually a common metric in marketing departments to look at the lift, which is a measure of the improvement that you can get from like an advertising campaign. It emphasizes the improvement over a low baseline, and that's because not a lot of people respond to advertising. For example, if you get like a direct mailer, they may mail out like 20 million mailers and maybe only like 0.0001% responds. But then if they do a new mailer and 0.0002% respond, they'll say the lift was 2 because they doubled the response rate. But it's a way to emphasize the improvement from a low baseline that arose in a business context. So that's how we do top decile lift. And now here's my summary of what are good and bad lift scores. Now there's also a measure which corresponds to random guessing in lift, which is the lift of 1, because that would mean the churn rate in your top decile is similar or the same as the churn rate in the overall population. So you didn't succeed in predicting anything in that case. So I kind of distinguish between low churn and high churn for what's a good lift case result, because it actually matters. So if you have a high churn rate, then the maximum lift possible is lower, and you'll tend to get lower lifts. If you have a low churn rate, then the maximum possible lift is higher. You can think about that like what would happen if you had all churns in the top 10%. Then your lift would be 1 divided by the overall churn rate. So that's how you can see that the higher the overall churn rate, the lower the maximum possible lift. So anyway, here I show that a lift of 4 is actually pretty good. 3.5 to 5 for low churn, or 2 to 3 for high churn is a healthy lift. Again, if your lift is too high, Probably something wrong with your model, because churn is not usually that predictable. Similarly, if your lift is significantly below 1, check your model. You might be taking the wrong column from the predict proba output, assuming you're using Python. So now we've got these measures of accuracy. Now how are we going to use that to fix our regression model? Remember, we want to optimize these measures. We're going to do testing of our regression model, and that we're going to use a technique I call backtesting. Backtesting is like cross-validation. So who's heard of cross-validation? If there's any data scientists out there in the chat, you definitely know what cross-validation is. But you might not know what backtesting is. What backtesting is a term for cross-validation that respects time. So I'm illustrating here, pretend all your data runs from January through June. Now, if you were to cross-validate this data, you would slice and dice the customers randomly into like a control group and a test group. But when you do backtesting, you actually respect time, and you form a test by fitting your model on the earlier time period and testing it on the later time period. And that will do a test which shows how your model predicts on customers it has never seen before, which is important for machine learning and regression testing. But this also respects the time dimension of the data. So, and then you can do another test. In this case, imagine, so we did our first test by training on January, February, and testing on March and April. You could do another test by training, you could advance 2 months and train on January, February, March, and April, and test on May and June. And this process of backtesting continues. Hey Scott, looks like Scott's calling it a day. Thank you for joining me. If that's a goodbye. So it looks like it's a what's up. I can't really tell. Anyway, so this is what backtesting is. Now, doesn't that sound kind of complicated? Oh my, and you're probably thinking like, oh my God, how am I going to code this backtesting? It sounds really complicated. Well, don't worry. sklearn has you covered. And we're going to look at a listing now which implements backtesting very easily in Python. So let's go in here, and I'm going to make a new config for backtest 9.3. So we'll do chapter 9, listing 3. And now you'll see how to run the backtesting accuracy measurement in Python. So we're actually going to use some classes from sklearn model selection. One called grid search CV and one called time series split. Now you will notice that there's not a class called backtesting in sklearn. They call it time series split, which kind of sounds like what I just described. You divide your data up by time instead of randomly. But they don't call it backtesting. I do. Why? Because I actually learned this as a Wall Street analyst. And on Wall Street, where they invented this technique, they called it backtesting. Then when whoever wrote the Python library, they wanted to make it sound more data science-y, so they called it a time series split. But anyway, let's see how to run this code by putting in a breakpoint and getting to it. Let's see. So as before, we're using our prepare data function right here. So we load the data and prepare it. Now I'm making next thing I do is I make a time series split object, which is the one that I imported from sklearn model selection. And what I'm giving it is the number of test splits, which in this case I set to 2 apparently, which is not that many, but this data history isn't really that long. So then you create the time series split object. The next thing we're going to do is make a scorer out of the lift, because we're actually going to backtest both of the accuracy metrics that I told you. We're going to look at both the AUC and the lift. Now the AUC is a default scoring algorithm for sklearn. So I put my scoring models in a dictionary here, and for AUC I just use a string. I say AUC This is the ROC AUC metric that we already saw. But for lift, I actually need to make a scorer object, which I do by creating this I use a make scorer function call, which I've imported here from sklearn metrics. Import make scorer, and then I pass it my calc lift function, which we just looked at in the last listing. So that was my own listing 9.2 calc lift, and I wrap it in the make scorer object so that I can pass it into the backtesting. So I put those both in a dictionary, which here I've called my score models. So this dictionary, it's a little bit funny. It has two elements, one of which is a string and one of which is an object, but it doesn't matter. That's how it works. I'm just showing you how to use it. Don't ask me why. So then I create my logistic regression object just like I usually do, right? So I'm creating my logistic regression object, and then I'm going to call this grid search CV. I'm going to make the grid search CV object. Actually, I'm not calling it. In this line, I'm creating it. I'm passing in the regression object I created. I'm passing in the score models, which is this dictionary I just created. And then I'm passing in my time series split object, which is telling it how to split the data. This is where you could also use a random split, which doesn't respect time. But for churn, I really recommend using a time series split, because real churn data, it's changing, your business environment is changing all the time. And that's why it makes sense to respect time when you're testing your model. It's the most realistic way to handle this. So let's see. This is saying that I'm going to try only one parameter, which is a C of 1. Oh yeah, Scott Edwards said no C. Here, well, in this case, I'm only trying one C parameter value, because here I'm still just demonstrating how to do this. I'm not actually testing multiple C parameters, which is next. So I'm just kind of like doing it in pieces. So let's just look at the result of the backtest first. So finally, I create the grid search object, and then I call the fit method on it. And that's really it. The grid search object is going to have this CV results data attached to it. I put that into a data frame to make it easier to handle. So here is the result data frame from my backtest. And it actually only has one row in it. So I'm just going to save it out, and it'll be easier to look at in Microsoft Excel. So this is the result of my backtest run here. We'll just look at that in 1 second. Hey, it's not opening. Come on. Here we go. All right, so there's a lot of outputs here. And that's why I'm starting it simple to show you what all these outputs are. So we have one row of data, and we have all these outputs that came out of it. This is from the backtest. The first thing it says to me, the mean fit time, 0.2 seconds. That's great. The first few things are about the timing. Next, we've got the C parameter that we use, which is the standard 1. Next, we see that the lift, remember we did splits, so there's 2 splits. The first split had a lift of 4.4, the next had a lift of 4.5, and the mean is 4.48. And next, the comes the AUC section. On the first split, we had a list of 0.77, the next split an AUC of 0.79, so our overall AUC is 0.78. And then these are like the standard deviations. So that is what you get from back testing with just at a single parameter value. In this case, C equals 1. But I've kind of been hinting that this is where we're going, is to backtest multiple C values, which is coming at next. So now we're talking cross-validation. And if you're already a data scientist, you definitely know that cross-validation is when you compare the accuracy using different parameters for your model, and you pick the one which is the best. So imagine doing I showed you just one backtest now, and we got the AUC for it. But imagine doing different backtests. And so in the first backtest, we might use one value for the C parameter. And on the next backtest, we might do another value for the C parameter. Another backtest, we might do the third value for the C parameter. And then with each of those C parameter values, we get a different value for the AUC. And then you pick the best one. Now, this is the standard approach for cross-validation. And the only thing that I'm doing a little bit different is that I used backtesting instead of, which is time-sensitive cross-validation, instead of time-insensitive cross-validation, which is like standard cross-validation, just random shuffling. So this is what we're going to do now, and that gets us to listing 9.5, which is kind of where we've been trying to get. So this is like the ultimate goal for today's stream, is to get to cross-validating our regression right here. I'll put a breakpoint in it here, and then we can we can run it as usual. So let's see, I'll duplicate this listing again. So this is 9.5. This is the regression cross-validation. I'm going to say reg CV, and this should be listing, I said listing 9.5, because you remember we did listing 9.4 earlier. So now this is combining everything we were talking about accuracy with what we were talking about the C parameter, because I'm going to test the C parameter for different values and look at the accuracy. So part of this listing, like with most of my listings, is going to be just running it. And the other part is going to be analyzing the results. So we've got the running part first, and then there's some analysis later. So let's go into it. So here we are going once again into regression running listing. And here we go. So as usual, we will prepare the data with the prepare data helper function. Just like in the last listing, I'm going to create a time series split object, specifying just a few splits for this simple example. Now, just like in the last listing, I'm making my score models. I've used the makeScore function to wrap my custom score, and I just use a string for the standard AUC. Now, once again, I make my logistic regression object. This time I'm doing something different in that I'm defining multiple test parameters in a dictionary. So this is the sequence of C parameters that I'm going to try. And hopefully you can see this small font. It's actually looking pretty small. But apparently no one's complained about the font being too small, so I guess it's not too bad. I think last week Maddie was like watching this on his phone, which you would definitely not be able to see this on your phone, but still. So you can see I'm testing a range of C parameters, and in each step I divide the C parameter by 2. So I start at 0.64, and then I do 0.32, 0.16, etc., down to very small C parameter values. And at each step I'm dividing the C parameter by 2, so it gets smaller and smaller, faster and faster. That's what's happening. So now I'm going to paste these into my test parameters, and I'm going to put those into my grid search CV, and then I'm going to call fit again. So this is really just like the last time, except I'm doing it for more C values. Oh, you're on your phone and you're nearsighted? Oh, cool. Wow, well apparently you can see it on your phone, Scott. I guess I'm using a big enough font then. But if it's not, let me know. I can always make it bigger. Alright, so now once again I'm gonna get my results from the CV, the cross-validation, I'm gonna put them in a data frame. Only now I've got multiple rows. So here I've got one row for each value of the C parameter that I used. And you can see that a lot of things, change. You can actually see the fit time gets shorter for lower values of the C parameter, and mostly the lift's the same. We can already see that at the very high values of the C parameter, the accuracy gets worse. Now that's the basic result for this, the cross-validation of the C parameter. But I'm actually going to do one extra analysis that I recommend for regression, which is to check how many weights you had. So here I actually have a helper function to test the number of weights for my C parameter. And this is a custom output. You don't get it from the standard grid search, but it's right here. All I'm going to do in this loop is I'm going to loop over my test parameters, take each value of the C parameter, fit the regression right here, and then I'm going to count, this one-liner will count the number of coefficients that are not zero. I do that by converting the coefficients into Booleans and summing them. So those that are zero get zero, a non-zero coefficient becomes a 1 in this sum function. And so this counts the number of weights. So I'm just going to loop over this, and for each value of the C parameter, count the number of non-zero weights. Because remember, that was an important output of this regression. We want to minimize the number of weights while maximizing the accuracy. So that's what we're doing here. And that's kind of it for that function. So I'm going to step out of this one. And now I'm going to save all those results to a CSV file. And then I do a plot function. I'm not going to show you. Let's look at the result first, and then we'll look at the code for the plot function. So I'm actually just going to let this continue, and let's go look at the results plotted, and then we'll see how I made the plot. So this is the plot of the regression cross-validation that we just ran. And here it is. So there are 3 subplots in this output. Oh, wait, what's Scott saying? He's on his phone. He's nearsighted. Seems good. Okay, anyway. So here is the result from running the regression on the social network data set. So remember, the regression C parameter, we started at 0.64 and I divided it by 2 until we got down to 0.0025. Now the bottom plot is actually a good place to start because that shows you how many non-zero weights we ended up with. So for the 2 highest values of the C parameter, there were 12 weights. Then when we get the C parameter down to 0.6, 0.08, there are 11 weights. Then it goes down to 9 weights that are non-zero, and then we get down to even fewer. And at the lowest values for the C parameter, there were only 3 non-zero weights. And we were seeing that. Remember, we messed with the C parameter earlier in today's stream, if you were here for that. And we saw that lowering the C parameter lower and lower gives you fewer and fewer non-zero weights. Now what happens to accuracy? Actually not much. The accuracy stays basically constant until you get up to the most reduction in weights. Like at this point you can kind of see that accuracy is going down, and here you can really see that accuracy went down. So by using too low a value of the C parameter, we actually reduced accuracy. Same thing for the lift. The lift stays kind of constant for most of the C parameter values, but when we make C too low, we lose lift, and we want to lift. So in this case, I would probably say to use C parameter around 0.02, which is shown here, because at this point, we haven't really reduced the accuracy. Maybe at this point, I don't know, somewhere around here, the accuracy is the same, but we went from 12 down to 9 weights. And reducing the number of weights is good, because it makes your regression less confusing. You want to reduce those unused weights. Now let's look at the output from the file. This will show you what the output of the cross-validation is in a file, because I saved this out too, so you can see all the different results. Let's see. So here's what you get when you use cross-validation with multiple C parameters. You get 1 row per C parameter here. It's also showing you these fit times, so those are not super interesting. It's more interesting when we look at the lift. So when you look at the mean lift here, you'll actually see it does look like the lift increases a little bit as you reduce the number of parameters, but not much. So it goes from 4.47, you can get around 4.5 lift at these parameters. And it doesn't really go down until you get really too high. Down here, the C parameter is gotten too low, too low. So that shows you too much or too little C parameter is bad for accuracy. Here's the mean AUC. And you can see it actually doesn't make that much difference until somewhere down there. So you can see the best values are, the first several lifts. Actually, it says the highest AUC is the second one. Must be a very small difference. Let's go back and look at the plotting function real quick. So I'm going to put a new breakpoint here at the plotting function, just so you guys can see how I did that. I'm going to run the same listing again, and we'll step into the plotting now that you know what the plot actually looks like. All right, I'm just going to go straight to my next breakpoint here. Whoop, too high. All right, so here I am. Now let's go into plotting the regression test. Pretty easy. So I've got a result data frame already. And here I'm just actually turning my C value into a string. That'll actually make the plot look better. That's like the messy details of plotting. So first I make a figure, which just appeared for me over here. And now I'm using matplotlib, of course. I use matplotlib as plot, like everyone for everything. matplotlib.pyplot as plot. And that's how we're going to do all the plotting. So I make the plot, and I'm setting a font size. So I make a subplot. I actually have a subplotting helper function. The first one is to plot the AUC. And that's how it goes. And then I add the title. And now let's go into the subplotting helper function so you can get a look at that. Here I use plot.subplot to make each subplot, and then I'm plotting the thing. I mean, I'm just reusing the logic to make one of these plots and then, annotate it. I turn on the legend, turn on the grid, and that's how I do each subplot. And basically I just keep doing that until I get the rest of my plot function. And that's really all there is to it. So it's not actually that interesting from here on. So that is how you do the C parameter backtesting. Hey, Deborgasm, yeah, you're late again every Saturday. I try to start earlier in the afternoon in the vain hope that a few people from Europe will stay up to watch. I mean, I know Maddie, he usually streams on Saturday, and sometimes he watches my stream afterwards. It's a little late for people in Central Europe. I figure this isn't too bad for England, at least when I start. So anyway, I start kind of early because I want to make it at least possible for someone in Europe to watch my stream, unless they're a real night owl. So anyway, I always highlight and save all my streams. So what did I just do? Let's see, I just saved out this result of the cross-validation, but you already saw this actually. We're already looking at this. Now actually let's go look at some real case studies. And we're just about wrapping it up, so sorry, Deborgism. Here are some real case study results showing you exactly the type of analysis that I just did. Now you remember earlier I said we wanted to maximize the accuracy and minimize the number of weights. But in the example I showed you, the accuracy never really went up. The accuracy only went down when the C parameter got too low. So by maximizing the accuracy, we just mean that we didn't ruin the accuracy by reducing the weights too much. But here in real case studies, you can actually see that reducing the number of weights does increase the accuracy very often. So here's a case study where when I reduced the number of weights to about 30% of the original, so this is showing the number of weights going down on a relative basis for the case study. So this is 100% of the original weights, and as I reduce the C parameter, the number of weights from the regression goes down, 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 and it's a little bit subtle, but the accuracy is actually increasing. So here you see that the accuracy increases until we've got about 30% of the metrics remaining. In case study 2, the accuracy also increases. You can see accuracy in terms of AUC going up, and it's at the maximum when about 65% of the weights are retained. So this was showing for real case studies that reducing the number of weights by lowering the value of the C parameter really can increase your accuracy. Now, it's not always the case, though, which is shown here with case study 3. Case study 3 had the lowest accuracy of all. And in this case, I found that removing any weights reduced the accuracy noticeably. I mean, you know, by using one value lower on C, you get a little reduction in accuracy, even though it only removed one, or, well, a small percentage of the weights. I don't know how many that is. But here, any further reduction in the C parameter just hurts accuracy. So you have to test. It's usually the case in real case studies that reducing the C parameter increases accuracy. Yeah. It is actually kind of weird. Lift is really non-linear and weird. So I actually advise to use the AUC to tune the model. Actually, that's a good point to mention, and I'm glad you brought that up. You might notice that whenever I set up my cross-validation, let's see, where do I say it? Where does it say it? CV equals TCSV, param grid. I thought I was telling it, telling it to use the AUC to pick the best value. I thought I was, I should be. Param grid. I'm actually not remembering this right now. I certainly did it in this other one. Didn't I? See here, oh, I'm saying refit using AUC. Oh, I'm trying to remember. Well, actually, I actually know what's happening here. I think I'm sorting it myself. I'm telling it to refit the best model using the AUC as the output. So that's so in the saved file, I actually save out both the AUC and the lift. And you can look at the rank. It shows you the rank according to AUC here, and it shows you the rank according to lift, you know, here. And the place where it really matters is, here when I said to refit the final model using the best value of the AUC. So the reason I said to go into that, why did I go into that whole diatribe, is that don't use lift to evaluate your model, because lift can be really weird and non-linear. Lift is good for explaining your model to business people, because AUC is pretty intuitive to me, I think, but to business people it can be kind of confusing. And lift is just a metric that business people are more used to. So that's why I say tune your model using AUC, then use lift to if you want to tell business people how accurate it is. But lift can be really weird, especially if you have smaller data sets. So watch out for using lift when you're fitting your model. And don't fit your model using lift. So anyway, so these are the real case studies demonstrating this technique in the wild world of real churn analysis. And I think that's actually all I really prepared for today. So yeah, it's been an hour and a half. That's about my usual streaming time. We got a good way into chapter 9. Yeah, thanks Scott. Thanks for staying with me the whole time and keeping the chat at least a little bit alive so I know I'm out there. So what do we go over today? Fighting churn is about making targeted interventions, improving your product, engaging with your customers, supporting them, all that good stuff. We talked about preparing a data set for regression. Actually, this looks like my old stream summary. I don't think I made a new stream summary. Oh no, I did. So we talked about logistic regression. Use the C parameter to control the number and size of weights, also known as the coefficients. Right. Then we talked about measuring accuracy, and I said don't use standard accuracy for churn because churn is a very unbalanced problem. And you can cheat on churn by just guessing that no one churns, because churns are always going to be a small percentage if you use standard accuracy. So use AUC or lift. Backtest to find the optimal values of the C parameter. Backtesting is a version of cross-validation, which is time sensitive, and we saw that today in the stream. Reduce the number of weights while optimizing accuracy. Although you may find that accuracy doesn't increase, you still want to reduce the number of weights as long as accuracy doesn't decrease. Because actually reducing the number of weights that come out of your regression, or the number of non-zero coefficients, it is an end in itself, just because it reduces the information overload from using your model. And I think that's it. All right, so that's the summary for today. Did you apply any oversampling technique on the training set? No, I did not do. Oversampling is something that you can do, and I think what de-Bourgasm is referring to is you might increase the number of churns in the data set. Because I said the problem with standard accuracy is that churn is rare. So one way you could solve that is just by duplicating the churners in your data set. And that would effectively, that's what oversampling means. You sample the churners more than once, or the rare group, whatever it is, in your problem. You can oversample them and increase their number in the data set. Now that would fix your accuracy measurement problem, but the reason I don't like oversampling for churn is for regression we're actually interested in a calibrated probability output. That's one of the things about regression, is the output, as we saw last week, let me go to that, is actually the probability. Let me scroll down. Last week we looked at this histogram. We produced a histogram of churn probabilities, right? And this is one of the outputs we want from our regression. And the problem with, so oversampling is great for machine learning when you don't care about the probabilities that you're spitting out. But if you want the probabilities you spit out to remain calibrated, you don't want to oversample. So that's one reason that for churn, I like to switch and use AUC instead of accuracy. So I keep the calibration of the data set while still doing a better job on the accuracy measurement. All right, so if anyone else has any questions, feel free to interrupt me right now. Otherwise, I'm just going to do my closing, basically my closing self-promotional stuff. In case you didn't know, the streams on Twitch start at 2 on Saturday. That's my live streaming time right now. I can only handle one stream a week. I just got too much stuff going on. I also post these all on YouTube. I don't know why I tell this to the Twitch crowd, because Twitch crowds usually hate on YouTube. Yeah, thanks, Scott. Have a great weekend and a great week as well. Thanks for joining. And of course, this is the book where you can find out lots of more details about everything I spoke about today. There's also a discount code, so please use the discount code if you are going to buy the book. But hopefully, watching the streams and looking at the source code on GitHub will tell you all you need to know to, use this code without buying the book, if that's your thing. And that's it. This is where I say thank you and goodbye. Please connect with me on LinkedIn or follow me on Twitter, because, Twitter is really where we announce streaming stuff. So definitely follow me on Twitter at Carl24K. And of course, you're watching Carl24K Data Science, so that's kind of it. So let's see, we have a few people left. Often at this time, I check if there's any live data streaming that we can go raid. Does anyone want to raid a live stream? Oh, I see. I will join early next time. Yeah, try it. What time zone are you in, de-Bourgasm? Are you in California or somewhere east of here? Bye, Alejandro Close. Now, does anyone want to raid another data or programming stream? I'm looking to see if anyone's live right now. There's usually no one streaming data after me, which is kind of a bummer. And my internet connection is sucking, so I can't even see who's live on Twitch right now. But if you hang out, well, I'm trying to check. If you have any, oh, Toronto? Okay, so you're a few hours ahead of me. Wow, Twitch is like not responding. That's messed up. Here's what I'm looking at. Having trouble trying to find that site. All right, I think Twitch is telling me that we cannot raid another channel today because I can't even see who's live. What the hell is going on, Twitch? Boy. The server not found. All right, I give up. Maybe it's telling us that we should go out and enjoy the rest of our weekend outside. For me in California, it's actually pretty nice and sunny. So I'm going to get the heck out of here, take my dog for a walk, do something like that. I think I'm going to one of those socially distant outdoor gatherings this evening. We'll enjoy some dinner outside. So hope you all have a good rest of your Saturday, good rest of your weekend, and a good week back at work or school or whatever it is you usually do. Thank you for hanging out with me and learning about data science and fighting churn with data this afternoon. So take care, have a good weekend, and hopefully see you all next time. Bye-bye.